Assalamu alaikum. In this video, we study implicit functions. Usually, functions are written like this. Y is equal to f of x. And this is a univariate function f of x, and that is equal to y. So this defines a relationship between x and y. And if we move this f of x to the left-hand side, we have y minus f of x equal to 0. So if we generalize this as a bivariate function, so instead of writing y minus f of x, let's write this as capital F of x and y equal to 0. Now, forget about this relationship and just consider, suppose we have this bivariate function from the beginning. Does this define a function like this? Sometimes yes, sometimes no. So this defines an implicit function, y of x or x of y. Let's put it in another way. Let's consider usual explicit function, y equal to f of x. Then consider the graph of this function. That is defined as a set in two-dimensional space where y is equal to f of x. So this is the graph of this function, right? So now consider this case. If we define a set x and y that satisfy this relationship, can this represent a graph of some function? Sometimes yes, sometimes no, as we have said before. For example, let's consider an explicit example. Suppose f of xy is equal to x squared plus y squared minus 1. Okay, if this is equal to 0, then this represents the unit circle at the origin, centered at the origin. So just let's draw the graph of this. So it's a unit circle. So the radius is 1. So this is 1, this is 1, negative 1, negative 1, and the center is at the origin. So is this a graph of some function? Actually, it's not. Because for any given, so x can vary from negative 1 to positive 1. So for any value between negative 1 and positive 1, there are two corresponding values of y. So the value of y is not determined uniquely, therefore this is not a function. For example, if this value of x is a, then we have positive value, that is square root of 1 minus a squared, and we have a negative value, that is negative square root of 1 minus a squared. Therefore, the set defined by this, f of xy equal to 0, is not a graph of any functions. However, with slight modification, we can make this represent a graph of some function. So we add one more condition, that is y is positive. Okay, so x and y satisfy this relationship, and y should be positive. Okay, in that case, then what this set represents is this part of the graph of this circle. Okay, and we do not include these endpoints. Okay, then for each value of x between negative 1 and positive 1, not including negative 1 and positive 1 themselves, then this represents a function, that is y is equal to square root of square root of 1 minus x squared. So this is the function represented by this part of the circle, this upper part of the circle. So a part of a curve is called a branch of this curve. Okay, so we may say this is a branch of the unit circle where the y coordinate is positive. And we can also define the negative branch. Let's see, this part. That would be y equals negative square root of 1 minus x squared. So this is another branch. Okay, so if we set this square root of 1 minus x squared as phi of x, let's name it. So if we replace y by phi of x, then x squared plus y squared minus 1 equal to 0 can be written as x squared plus phi of x squared minus 1 equal to 0. So if we take any point on this unit circle, let's say where the point is above the x-axis, that is y coordinate is positive, then we can find, in this case, we can find a function phi of x, such as square root of 1 minus x squared, that satisfies this equation. Okay, so let's write it using this f of x and phi of x equal to 0. Then this function phi of x is called an implicit function of this capital F. Okay, so this is called implicit function. And of course, negative square root of 1 minus x squared is another implicit function of f in this case. Okay, let's give a more formal definition of implicit functions. So here's the definition. Y equals to f of x, a univariate function, is an implicit function of f of xy equal to 0. So what this means is the following. F of x and phi of x is equal to 0 for all x in the domain of phi. So domain of phi is where this function, the range of x that on which this function is defined. Okay, so that's the definition. And in the case of this unit circle example, the domain of phi is between -1 and +1, not including -1 and not including the endpoints. So in the case of x squared plus y squared minus 1 equal to 0, so that's f of xy, the implicit function is either square root of 1 minus x squared or negative square root of 1 minus x squared. And the domain of phi is the open interval between -1 and +1. Okay, not including the endpoints, because at the endpoint, this tangent line becomes vertical. So this is not a function. So we cannot define an implicit function at these points. Next, we give an important theorem called Implicit Function Theorem. And the proof is given in another video, so I will just state the theorem here. So let f of xy be a function of C1 class and defined on an open region, U. And suppose a point P, AB, satisfies the following condition. That is 1. F of AB is equal to 0. That means this point is on the curve defined by this function. So f of xy equal to 0. And 2, the partial derivative of this function with respect to y at this point is not equal to 0. Okay, then we have the following. Then there exists an open interval, I on the x-axis, such that A is in this interval, and also exists a univariate function y equals to phi of x defined on I, such that 1 f of x phi of x is equal to 0 for all x in the interval I. Okay, so that means phi of x is an implicit function of f xy equal to 0. And 2, b is equal to phi of a. And also we have phi prime, that is the derivative of phi with respect to x, of course, is equal to negative the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. Okay, that's it. If we assume the existence of the implicit function phi, then this last equation can be derived very easily. That is, if we differentiate f of xy equal to 0, actually let's replace y with phi of x equal to 0, and let's differentiate this equation, both sides, with respect to x. So using the multivariate chain rule, and this x is considered as a function of x, so it's a trivial function, and this phi of x is of course a function of x. So if we apply the chain rule, then we have a partial derivative with respect to x evaluated at this point times dx plus the partial derivative with respect to y evaluated at this point, and d phi dx equals to 0. Okay, then this one is of course equal to 1, so we can just get rid of it. and move this to the right hand side and divide both sides by this, then we have d phi dx equals to negative this thing, so that is fx, and divided by this thing, that is fy. Here, as we have seen, we are assuming that the partial derivative with respect to y is not equal to 0, of course. And since we are assuming that this function is of class C1, so that is continuously differentiable, therefore these partial derivatives are continuous. Okay, and since we're assuming this, so this partial derivative at AB is non-zero, then if we choose an open interval that is small enough around the point AB, then within this interval, this partial derivative is also non-zero. Okay, I mean, we are actually choosing this interval so that this is non-zero within that interval. Therefore, this equality holds. Okay, let me explain what this implicit function theorem means by a simple example. Consider a function like, or curve like this. So let's see, x and y. So suppose we have a curve like this. Okay, and let's say this is point P. So in this curve, the partial derivative with respect to y is non-zero because it's not vertical, right? So if we choose this part of the curve, okay, then within this interval, let's name it as I. So this is the interval I. So within this interval, this yellow region can be considered as a function. The yellow part can be considered as a function of x. Okay, so that is y equals to phi of x. So in a sense, we can extract a certain part of the curve so that that part can be considered as a function of x. Okay, but this part, let's call it q. At this point, the gradient and the slope of this tangent line is vertical. So around this point q, we cannot define an implicit function because this violates the condition, one of the conditions here, this one. So it should be non-zero. The partial derivative with respect to y should be non-zero, but at this point, that is 0. And similarly, at this point, let's call this r. Again, this tangent line, the slope is vertical, so we cannot define an implicit function around this point. However, for other regions, let's say, for example, here, it's okay. So around this point, we may choose some interval. For example, this big. We can define another implicit function here, or here, or maybe we can extend that to somewhere here, like this. In the case of the unit circle example, we could find the explicit form of this implicit function phi, but in general, it's not possible. So we just know that implicit functions exist, but we may not be able to express that function explicitly. That is very normal. And you may be wondering what So what can we do about these points such as Q or R here in this example, where the slope of the tangent is vertical? In that case, instead of considering y as a function of x, we may consider x as a function of y, as long as the partial derivative with respect to x is non-zero. Okay, so instead of y equals to phi of x, we may find some function. So instead of this, we may find something like x equal to psi of y, that is a function of y. So x as a function of y. As long as the partial derivative with respect to x at point AB is non-zero. Okay, so the roles of x and y are swapped. Okay, so in this case, this cannot be zero because we divide by it. But in this case, this cannot be zero because psi prime of y is, so by symmetry, we should have something like this. What is psi y, y, and f of fx psi y and y. So this cannot be zero. But so as long as one of the partial derivatives is non-zero, then we can find implicit functions, either a function of y or function of x. But what if both of the partial derivatives are zero? Then in that case, there is no possibility for finding an implicit function. In such a case, we call that point a singular point. Okay, so let's define it. PAB is singular. So what this means in this context is that fx of AB is equal to fy, so partial derivatives, AB is equal to 0. So if the point is not singular, then the point is called regular points. Okay, singular points and regular points. Let's see an application of implicit function theorem. That is to find a tangent line of a general curve, or defined by f of x and y equal to 0. Okay, so suppose we have some curve that may not be given as a function, but we might want to find a tangent line at some point, let's say AB. Okay, P equal to AB, and we want to find tangent line at this point. Okay, so if an implicit function exists around this point, then let that be phi of x. Okay, then using the usual formula for the tangent line, we can find the equation of the tangent line, that is y minus b and phi prime at a, x minus a. So this is the equation for the tangent line. Tangent at AB, right? But from the implicit function theorem, this phi prime is equal to negative fx AB divided by fy AB, right? So if we move this to the left-hand side and multiply both sides by everything by this fy, then we have fx AB x minus a plus fy AB and y minus b equal to 0. So this is the general equation formula for the tangent line of a general curve given by this at point AB. Okay, so this is obtained assuming that we have an implicit function y of x, okay, phi of x. But if we don't have such an implicit function, but instead we could find an implicit function as a function of y, then we have something like this. So x minus b. So let's see. Suppose at this point, for example, at this point, we cannot define an implicit function of x, but instead we can find an implicit function of y, right? So let's see, change the color. So around this point, we may have an implicit function of y. So x is equal to, so this is x equal to something like phi of y, some function of y, right? So in that case, the tangent line is given as this, b, y minus b. But by the implicit function theorem, we have this. So move this to the left-hand side and multiply both sides, everything by this. Then we have actually the same equation. So either case, as long as the point at which the tangent line is obtained is a regular point, not a singular point, then the tangent line is given by this equation. Let's see a concrete example. F of x is given as, say, y squared minus x cubed plus x equal to 0, and try to find the tangent line of this curve at 2 and square root of 6. By the way, this point should be on this curve. Let's check that. So let's see, x is 2, so, and y is square root of 6, so y squared is 6 minus 8 plus 2. That should be equal to 0, right? So yeah, that is 0. So this point is on this curve. Okay, let's find the tangent line of this curve at this point. So first, differentiate with respect to x. That is negative 3x squared plus 1. And differentiate with respect to y. We have 2y. So if we substitute these values, we have, let's see, 2 negative 11. And substituting this, we have 2 square root of 6. Okay, so the equation of the tangent line is given by negative 11 x minus 2 plus 2 square root of 6 y minus square root of 6 equal to 0. So let's simplify this. We have negative 11x plus 2 square root of 6y, and let's see, 2 times 6, 11, 22, that is plus 10. Okay, and okay, so this is the equation of the tangent line. Let's make the coefficient of x positive, so that is 11x minus 2 square root of 6y minus 10 equal to 0. That's it. That's all for this video. See you later.